Hi, thank you, Priyanka, for the introduction. So I'll make some assumptions during this presentation. I'll assume all of you have some basic idea of what deep learning is, whether you've done it through Keras or PyTorch. I assume you have some knowledge of what a recurrent neural network is or what an LSTM is. And one more thing, I'll assume you know what an embedding is and or what to work. And if you haven't heard of these things, fine, I have a one-slide introduction for you. Essentially, an embedding is a way of transforming a text or token into a higher dimensional vectorized representation. And what happens is similar words end up having close proximity in that n-dimensional space. So having said that, we can start looking at what transformers are. So here's the outline. First, look at machine translation problem, where the concept of attention first came up. And it's also called encoder-decoder attention. And then we'll look at self-attention and the transformer architecture. And then we'll look at BERT, which is a bidirectional encoder representation, which came out after that transformer paper. And GPT as well came out around that. We'll look at both of them with GPT, just a slide for it. And then we look at the transformers library, which actually implements the BERT transformers. And you can actually go through a code sample to see how it's used. And we'll cover other applications of BERT or transformer architecture as such, attention as such, in outside of this domain of NLP. It's being applied to visual domain as well. Then the question and answers. So word to vec, I just talked about it, but these representations are discrete symbols being encoded into vectors, and they're not enough. So the first example here is these three sentences. The word face has slightly different meanings in the three sentences. So even if you had a single token representation with one vector, it would not exactly represent the meaning. It changes based on context. It changes because words start interacting with each other. And so when we disambiguate, we need to look at the wider context. We need to look at the interactions. And sometimes these interactions can be non-local. They're not just the next word. They're far away in the sentence. And there's one more thing. How meanings combine depends on these meanings. And to quote Felix Hills from DeepMind. So example is, let's take this phrase, kya baat hai, great. Kya baat hai means what is the matter, but in this context, it means excellent or wonderful. So the context has changed the meaning of the phrase. So any deep learning model or any model you feed in these tokens, they're not going to be enough because discrete tokens will not capture true meaning. So your model will also not be very accurate. So thing is, if this is the problem, so what can we do? So let's start with this case of sequence to sequence machine translation. I'll take this as an example of developing this concept of attention. So here what's happening is this: there are a bunch of RNN blocks or LSTM blocks on the left side. It's being fed in text in one language, say English here. The weather is nice. And the last block, the last LSTM block, in this case I don't show all the blocks, but the last block, it has a hidden context, and that's being passed over to the decoder side to initialize the first block there with that context. And I put in a start token to that decoder as input, and the output of that decoder is the translated word. Then I take that translated word, feed it back in, and I have now two words, start and ill, and then I say give me the next word, and it keeps generating the full translation and stops. So this is what was used for translation around 2014 time. And there was a problem with this. The problem, actually, there were two problems with this. One was that very long sentences, the state that you're using, one single encoder, one single context of that LSTM block at the very end, that's not enough to capture the long sentence. And so the emphasis would be placed on the latter half of the sentence. So that's not very good. The second thing is this whole thing is not parallel. This whole thing is one word at a time being fed in and one word at a time being translated. So it's what can we do here? Let's see. And before we solve these two problems, let's look at another problem. And this, if there is one slide that you should pay attention to in this presentation, and that's the simplest one, is that builds this concept of attention is when you translate, you have one language, let's say English on the top, and you're translating to French on the left. And when you are generating a token or a word on the left side in the new translated language, you are doing this, not like linearly that the first English word maps to the next first French word. It's obviously the ordering is changing. So if the ordering is changing, every word that is being generated on the translation side, it has to pay attention to what words it should use to decide, okay, what should be the word that is output at this point. So here the black side blocks mean that there is no attention being paid, and the color indicates how much attention is being paid while translating to the input text. And as you can see that every every text being generated, it pays attention to perhaps one or more input words. And so there's this concept of attention already that is developing. It's very intuitive here. Um, so the question is that the ordering is a problem, alignment is a problem, and we have to figure out how to pay attention to the input. So that said, what can we do? Now, one thing that people thought was in 2015, Badanu's paper, one thing they thought was that let's look at all the encoder hidden states when I'm taking in my English text and I'm translating. Let's look at all of them, whatever state they have, and let's try to do some kind of a weighted average. And that I will use, and I'll take that in, and I'll take my current hidden state in the decoder side, and then that'll tell me the next word to generate in the decoder. So in some sense, it is kind of trying to address that problem in the previous slide where we need to know what words in the input text we should pay attention to and to by how much. And so he tried this out, and essentially then the problem is how do we discover these weights? Now, these weights should add up to 1, obviously. So how do we get to that? So this is what they came up with. They said that let's try to build these weights, use some scoring function between the output context of the decoder, current context of the decoder, and all of the input encoder states. Let's try to build some scoring for all of these states, comparing it with the decoder's current state, and then use the softmax function and assume softmax will convert any kind of numbers into a probability, so which all adds up to 1. So these weights alphas add up to 1. And the next line, the context vector in this case, is just a weighted representation of all the input states. So we've kind of successfully handled that problem of alignment here by getting that weightage, how much weightage to give. And it's changing for every word as the HT is the state of the decoder. As the decoder is moving from one word to the next, you need to recalculate this alignment and figure out how much emphasis I pay to my internal states. So it shifts on which words in the input are being attended to. So people have tried different ways of calculating this scoring function, and this particular approach, now what we have settled on to is different from what was initially thought. People tried different things. They said, let's add up the vectors, let's do a dot product and scale the dot product. And that's what we've settled on. We've said, simplest thing is do a dot product between the state of the decoder, hidden state of the decoder, and the hidden state that is learned, the context that is learned by averaging all the input encoder hidden states, weighted average. So, and the later paper by Vaswani, the transformer paper, actually said let's scale it down because they had some problems with the gradients becoming too weak after the softmax. So they had to do this. I can talk more about it later, but these are the ways you could generate the weights, and you could then pay attention in a different sense to the input translation, input text, language text. Now we've solved one problem, long sentences, we've solved the problem. We still have not solved the problem of the inputs coming one sequence at a time. We have to be parallel. Now, how can we do that? Now, let's introduce another concept. Now, so far what we have done, it's called encoder-decoder attention. The decoder is varying for certain keys in the input and saying, okay, which ones match the best to my query? And that will be the highest weight, and I'll look at those. But let's say a string itself is being fed into a network. Imagine like something like a convolution operation is a new operation called attention is being defined, where I call it self-attention, where each token pays attention to the other tokens which are present in that sentence. Just like you do a convolution, you know that some parts of the image will kind of combine with other parts and give you some output in activation. Now, so could we do something similar what we did in the encoder decoder attention, where given one token, like say the sun, we know that the sunrise is a very related word. It should pay attention to that. Could we say that when we build out these attention vectors, we could do something similar where we have certain weights which we learn through a softmax scaling perhaps. And then again, it's some kind of a dot product. Intuitively, it feels can we try the same thing like what we did in the encoder decoder attention? And so indeed we can try that. And so we do need now, we do need that some kind of vector that we can use to do dot products with. Like, could we just take the embedding and do a dot product of one embedding with another? The thing is, last time we had different values for the decoder's hidden state and the encoder hidden states. So we could consider that. But let's try to do something similar by first taking the input and transforming it through some weight matrices. I mean, if you are Keras person, it'll be a dense layer. Pass this through a dense layer and learn some matrix that when multiplied with gives some output. If you are a PyTorch person, it's the NN linear operation. I'll do an NN linear on this input. And so I'll learn certain matrices, WQ, WK, WV, which when multiplied to the input would give me three vectors, Q, K, V. And Q is that query, which I will use to query for certain keys I look for in the other tokens. And then if the query is a good dot, if the dot product is high enough, I will multiply the dot product with the, once I scale it with a softmax, I'll multiply the value vector and pass it upwards. And let me show this in a better way because, yeah, so here's what I've done. So I've taken a token, the word the has become, and the gray thing is the embedding here. So I've learned the word2vec embedding for it or glove embedding for it. And then I have multiplied it with through a dense operation. Some matrix has been applied on it. It's a transformation. Three matrices, three dense operations, or three NN linears in PyTorch. I get three vectors, Q, K, V. These are learned, just like in convolution, you learn the weights of every layer. So I've learned these. I don't know what they are from upfront. Now what I do is I have my Q vector, which I'm going to use to now look for matches in dot product with all the other keys I have for the other tokens, including my own token. So the word pays attention to itself as well. So Q1 is the first word's tokens query vector. Q2 is the second token's query vector, like that. But Q1 is now paying attention to all the keys, K1, K2, K3, K4 for all the words. And we get a dot product. And we know that after this, we can do the same thing with Q2 and so on and Q4. And you know very well that these things are not done linearly, like all these things in a GPU will be all single matrix multiplication. So we can figure that out. It'll be one large Q matrix consisting of all these Q column row vectors, and we'll do the dot product all at once. Now we've done the dot product. We need to scale it. So we're using softmax, just the way we had done it from in the earlier case. And so we've got now a scaled weight. And now if I take the value vector, usually the keys and values are identical, but just, it's possible they could be different, but I push the value that I want to push up to the next layer above. And I scale the value vectors, which I also have learned, multiplied by these lambdas, the weights that I've learned using a softmax, and push it up to the attention vector. And now I have created a weight representation where every token now has not just its own discrete symbol encoding, like it started out with. The gray one is the word2vec encoding, but it's added in some amount of, it's paid attention to what the other words had, and it's added in some sense the weight meaning of those words into its own attention vector that it has learned. So this whole thing, after it has learned this, we pass it through another dense layer or feed forward layer. And this whole block is known as a transformer block. And because what I've done is each word here is now paying attention to the other words, and its meaning is not just its own discrete symbol that the embedding was. It's now blended in with a little bit of meaning from the others. And here's an example, like the sentence is this: the animal didn't cross the road because it was too uh, uh, too too tired. Yeah. So in this case, because it, what is it? It is the animal, of course. So if you see that the word it has to incorporate some of the representation from the word the animal into its newly learned high level representation, which I can then process in the higher levels. And that will actually carry some of the meaning of the word, that it is an animal. It's not just something. Um, this part, if it is not clear, just if anybody send, are there any messages? If it's not clear, I can repeat this. Okay. All right. So this.
Sorry, Anirban, there are a couple of other questions regarding the content, but nothing about the clarity of
Okay.
the
Okay.
slides.
All right. Okay. So now I have done one attention pass, right? That's a one transformer block. Now, if you know convolution operation, there are many convolution layers you can learn in, like, right? You have many layers, like, so can I have similar thought that can I have multiple heads of attention? Like if I'm recording sound, if you've done any recording work, you'll know that you will have a different kind of mic for a vocalist, you'll have a different kind of mic for percussion. These are paying attention to different frequencies. And so can I have, these are like almost like a multi-head 8-track recording, or so it's like a multi-head on passing through the text. And they're paying attention to the same word being connected with different words. And then when I first learned this, my thought was, what if all these heads end up learning the same weights? What is the point of it? Because but the same thing can happen in any neural network, right? That what if all your the same input is passed to all your nodes in the neural network, the first layer. Why don't they all learn the same weights? And sometimes perhaps there is redundancy. So if you randomize, you will end up having different weights being learned. So each layer will pay, each of these heads, it's not a layer, sorry, each are happening in parallel, and each of these heads is paying attention to different parts of the sentence when kind of associating it with the current token. So multiple contexts of that word can be handled in this way. Okay, so it's a multi-head transformer block now. Now the block that we learned, that whole thing, it's this thing in orange. Now I'm introducing this transformer architecture, and it's this thing in orange here. There are three kinds of attention happening in this transformer architecture. This is, again, this architecture was proposed to also do translations, but it's kind of solving your parallel input problem, because it's able to read the whole sentence together and kind of uh, relate each word to each other. So here's what is happening. On the left side is the regular self-attention in the orange block that you see. It's taking in some input and it's passing it through. There are other things I'll explain, these links and all, and positional encoding, I'll explain those. And it's doing that attention operation, which I talked of. Post that is there is a, like a, some normalization going on. It's layer normalization, not batch. Essentially, the features within are kind of normalized. All the features are normalized. And then next, again, it's that feed forward layer I talked about. And then again, there's some script connections, and then that's the output of that transformer block. And you stack up these blocks one over another. And on the left is again that encoder piece, which we encountered in the regular translation problem, but it's reading an input all at once. And on the right is the decoder piece. And the decoder is a bit more complex, because the decoder again has an attention, encoder decoder attention block, which is what we started with, that the decoder is paying attention to the input coming in from the encoder, and it has to decide how much weights to pay attention to solve that alignment problem. And then there is something below, which is masked attention, which is essentially the decoder has already generated some text, right, in French, say. So it has to pay attention to the words it has generated, and it has to pay attention to what is coming in to generate the next word. So that attention it cannot look into the future. It doesn't know what the next French word is. It's not generated yet. So it has to be cleverly masked. And what these guys did is essentially, if you add in a very large negative number before this softmax step, where the weights were kind of that the weights of the dot products were all passed through softmax. If you pass in a very large negative number, the softmax will make it output as 0. So you will not. So what they do is they put a triangular matrix with almost minus infinity for the words in front of the sentence that have not been translated. And so that softmax will say make it 0. So you won't pay attention to those words. So essentially the same architecture of that transformer block can now be used to do this masked attention concept. And so it'll only have, okay, these are the French words I've generated and this is what is coming in. And so this is the attention I do with the existing words, pass it up and go like that. So the 3 blocks of attention are there and they're kind of all different. So it's an important point here. And so there's some skip connections here, right? And the skip connection, remember I talked about this, how meanings combine depends on those meanings. So the only point you'll know all these words that have been used in the sentence is at a higher layer. So you need to have processed everything. And at that point, if you have a skip connection, then there can be some interaction possible between the higher layer data and the lower layer input, raw input. And they can kind of interact and learn, make an interpretation correctly that, oh, this means wonderful, not what is the matter. So this is the reason for these skip collections. And normalization just makes it converge faster. So we've basically learned this encoder, decoder, transformer architecture. And what happened at this point is people started splitting it up into pieces. Some people went on the left, took the left encoder block and started doing some work. And some people took the decoder alone and started doing some work. And so the whole family of architectures evolved after this point from this starting point. And so, sorry, I'm going back. One thing I forgot that whatever I talked about, the position of the words also matters, and the meaning changes based on that. And I didn't mention that position was factored in calculating the weights of how much attention to pay. And so in this architecture, position matters because we're reading in all at once. And so we had to add a position vector, and they kind of came up with some scheme where each bit there'll be a position vector calculated, which will depend on the position of the word, as well as it'll have each bit be taking some kind of a sinusoidal value between -1 and 1. And if it's an odd, it'll be a cos. If it's an even, it'll be a sine function. And the wavelength of it's basically a varying wavelength so that the words pay attention to some word far away from itself. And the wavelength varies from 2 pi to 10,000 2 pi essentially. And what I saw is you could implement the higher dimensions to be slowing down and having a very wide, slow wave, and closer dimensions to be watching nearby words. So each of these bits, if you see this position vector, each of these bits, each of these is having a different value, and it's basically paying attention to words nearby, or the next bit is going slightly further away, like the last bit would go 10,000 2 pi away, like the wavelength slowly increases. So it's kind of a hack, but it kind of works. Okay. So the performance of this is it's obviously n by n, right, n squared, because each word is paying attention to itself. But later on, the other thing is the D, the input dimension, is also pretty large. Sometimes it is maybe 512 or 1024. So D is not small. So even the recurrent thing performance was not too less. But what is happening is now even this n squared limit has been kind of addressed through there is a network called Performers, which is factorizing the attention metrics into 2 different matrices, and that way it becomes almost linear, and they're using it for protein folding. And then there is a reformer, which we'll come to a bit later. So let's talk about GPT because it came out after that. And so the GPT took the decoder side of that transformer architecture and broke it away and said, okay, I'm going to have mass self-retention. You give me one input, and I'm going to just, given some words, I'll generate the next word. And you know this GPT-2, GPT-3, the whole family, it works like this. And you can use it, and it's only decoder blocks. And I think GPT, GPT had 117 million parameters. GPT-2 has 345 million parameters. And so uh, it used to take in, it can take in, I think, 1024, and this must be GPT-3. I'm not sure how 4000 came. I have to check this. I'm not sure of this. But here the encoder decoder attention has been removed. It's only decoders and the mask self attention. So that's the piece that you have to pay attention to. And so post GPT, there's something else that came out. This is okay. Before that, this is how GPT works. You can use it for classification. You just give a start and end token, and you set the text, and you connect the output to a linear network, and you can say, send whatever this kind of document or not. Or you could use it for whether a premise and hypothesis are actually matching. Give a hypothesis, and you see if the passage has that. And again, it will you will have to separate these with start, delimiter, and end tokens. And similarity of sentences. All this was achievable. Um, Post this, I mean, BERT, similar time, BERT came out, and BERT is a different approach. It has taken the left side of the transformer architecture. It has taken the left side of where I have an encoder and those transformer blocks which we had seen before. There's no masked attention concept here. It's there are initially I think they had 12 layers and 12 attention heads, and it had 110 million parameters. And basically, you start with a classification token. You give it a string, you have a separated token, you give it another string, and it can do some processing. For example, it can tell if these sentences are connected sentences or not connected. And so what did BERT do actually? BERT is it's like what VGG16 did to ImageNet. It's created a pre-trained natural language processing model, which is huge because till this time you would have to train on a corpus. You would have to have labeled text. I remember when I did search, I had to classify text for better relevancy, and it was very hard getting text, labeled text. You get very little. So the advantage with this is that if you have a pre-trained model, just like VGG16 or ResNet, you now have something to work with. You just tune it for your task, and that's it. You can do a lot. It's a pre-trained. You will tune it much faster, and it's so usable. And you don't need the resources like a TPU on the cloud. This took 4 days on 4 TPUs to train initially. So it's it's very hard for somebody to train from scratch a full language model like this. Uh, so how did BERT get trained? So BERT was trained where the input tokenizer randomly marked 15% of the input tokens for omission, like 15% marked, and so of those 80% of the time it was replaced with a mask token, and essentially BERT will have to predict what the mask value is. And 10% of the time you replace with different word, and 10% you keep the same word. And you need to do this because if you completely leave it clueless, that it won't learn. It needs some assistant. So you sometimes keep the words in there. Um, so with this is one of the tasks that BERT was trained on, and they're feeding whole of Wikipedia and some, I think, some other books corpus as well. And it was 16 GB of data, I think, that was put in. And post that, um, the other task was also sentence level training. Like you have one sentence and you have a second sentence, and the BERT has to predict. And this is like a simple binary value, whether it's what is the probability that the next sentence is truly following the previous sentence. So BERT is able to actually learn English because it's been trained on how sentences are framed, how words connect, and how sentences follow other sentences. So even some idea of passages. So once it was trained like this, you could end up doing many tasks. Like you could do Squad is the question answering data set of Stanford, and named entity recognition. You could do anything. Um, so I'll kind of cover, but some idea of it is essentially I could give the question in I could give the first text in one place, and the top leftmost token, the classification token output, could be a vector that I feed through a dense network, and it'll tell me whether the classification is of this kind of document or that kind of document. Or I could kind of tag every piece of each tokens. I could kind of tag and say this is a verb, this is a noun, this is a predicate, all that. And I could also give question and answers and say, is this question, is this answer correct? All that. So, and it has been used for summarization also. I could take these output of these classification tokens, and then I could do some kind of clustering around them. So all similar sentences would end up in the same cluster, and I choose only the centroid of it. And so if I have a k-means, I do 5k, I'll have only 5 sentences to summarize the whole passage. So you can do things like that, and it's pretty much available on the web. You can see these examples. Um, so the difference between BERT versus GPT-2 is that actually there's one small mistake. The encoder decoder shouldn't be here, but there is the concept of mass self-attention in GPT, which is not there in BERT. So, and this is how the evolution has happened. That I mean, it's further gone to GPT-3, and it's got into billions of parameters. But as you can see, it started with word to vec and uh, Elmo, and then GPT and BERT, and 84% accuracy is what you will get. Glue benchmark is the general language understanding benchmark, and on the right side you see the complexity of the parameters. It's just started to shoot up. So actually, the other things that are not covered here, GPT-3 is 175 billion parameters, and then there is the T5 from Google, and Microsoft Research also had something. They're all, I think it was over a billion also there. So now it's a whole family, and there are simpler versions also like Distilbert, and there's a Facebook version, Roberta, which was, I guess, more complicated than Word, 4 times, I think, time to train. Um, so now we come to the application side. Okay, so how can I use BERT? So there is a library called the Hugging Face Transformers library. That's one way you could use BERT. They have these models, the BERT. Distilbert is a much smaller version. They have GPT as well, and they have the reformer, longformer models as well. Um, so the URL is here. You guys can look at this. Here they have the three main classes are there's a tokenizer, and then there's a transformer, and these are the heads. Now heads is don't confuse with the heads in the attention model. These heads are essentially like you want to do classification work, you want to do summarization, so next word prediction, so language modeling is that's what is called. So these heads are about that. So these are the heads. So you could do language modeling given x n minus 1 up to that, give me the next word, and sequence classification, queuing, question answering. So given an input, BERT could give out, given a question, as in the passage, all these tasks are available, but how do you input data to BERT? So if you want to input data to BERT, you need to make sure of these things that, there is this, you have to add this special classification and separator tokens. And then there is, it has to have an input mask saying, if all the sentences are not going to be of the same length. So if say 40 characters is the total maximum sentence length and one is 20, the other 20 bits have to be, some way indicated as not part of the sentence through this input mask. And there is another mask to indicate if, since there are two sentences that BERT can take in, like after the separator, the second sentence can come. So to distinguish which part of which segment it is, you need to have another kind of set of masks. And all this is kind of available in the Transformers library, but I'm just kind of mentioning it here that you need to do this. And I'll do a demo anyways, but I'll come to this demo a bit afterwards. Okay. So let me finish off this transformer architecture and the application. So as I said, that that n squared problem remains with this transformer. That since it's as n becomes too large, if you start going beyond Wikipedia articles, what if I had to generate like I have to read a whole book text and do some kind of summarization on it? Then the n is very large. It's no longer a Wikipedia article of 2000. So they started doing a simple hashing. It's called locality sensitive hashing. So by hashing that, the similar meaning words became transformed and be mapped into the same bucket. The blue ones all have similar meaning, related meanings. And so the LSH bucketing kind of gave you a transformation which made them all move closer. And post that, like they started, attending within the same bucket and in the nearby buckets. So this is one approach that was taken. And as I talked of, there is a performer architecture. Please look it up on Google if you want to look. They used it for protein folding because proteins and viruses are also, by the way, just sequences, right, of digits. So So of strings. So you can try to do simulations, and they're very large. Like they're almost a billion character strings. So you may need something different. And so they did Performer, where this did a factorization and split into matrices. You can look it up. And this can handle 1 million words and fit on a 16 GB GPU. This is amazing that it can do it. You don't need a TPU and all. And they also had a concept of residual layers where the gradient calculation requires activations to be saved for previous layers. And there were too many layers and too many activations adding up. So that became a constraint on the memory. So they kind of did some reversible layers where you didn't have to save the activations of previous layers. You could actually get them back. So that was another accomplishment. So that is pretty much the architecture side of what I will cover. But now there are other applications beyond natural language processing. And what's happening here is people have started applying it to vision. And Facebook first tried it. They did, they took, initially they had convolution networks. They did it for object detection. And they said that they got pretty simple architecture and similar comparable results as state of the art. And the latest paper, this is from this year, and it may not be still out officially. It's directly taking the images and not passing it through any convolution network, and then just splitting it up into smaller pieces and then turning them into like a one-dimensional vector through some linear transformation, that is the dense or linear layers. And then it's feeding it into this and trying to do a prediction of what class it is. So again, very similar architecture of multi-head attention you can see on the right. And you can look this up in detail. I won't go into the detail, but it's then, so you can see very interesting here on the right that the input image, the attention mask is actually able to focus in on the right object, the face of the dog or the airplane. It's actually able to sense it. So the other application is forecasting, where you can actually use it to forecast, because again, concept of attention can be used to different parameters. If I had say electricity demand generation, I wanted to forecast, I will not have the softmax at the last step, which I had at the encoder, in the decoder encoder architecture. At the last step, I have to predict the word to output, and I have a vocabulary. So I do a softmax, I get a probability. At the very end, I try to say which word has the highest probability in my vocabulary. I output that word as the translation. But in this case, I don't need to do any softmax of probabilities. I'm predicting a raw value, say, of electricity demand. So I could feed in data of electricity, past data, and actually it will fit it quite well. So you can try this out. I think there may be, if you say attention model electricity generation, if you Google for it, you might find an example. So it has been used for lane share prediction in self-driving vehicles as well. So that pretty much completes my presentation. I'm a bit late, I guess, but I want to do a quick demo around 5 minutes. Is it possible still, Priyanka?
Yeah, absolutely. We still
Okay.
have about 5 to 10 minutes.
Okay, all right. So this demo is actually by this guy who's written an article, the illustrated transformer. I just copied it over and changed it a little bit to add some more comments. But he's trying to do sentiment classification, right? And what he's going to do is, these are like examples of sentiments, positive or negative. And I think he has a data set of 2000 that he has created. So he's loading the pre-trained distilled BERT. As I said, distilled BERT is small enough. You can actually work with it and get, I think it's usable, quite usable. So he's loading the classes from the transformers library. This PPP, I think, is import transformers as PPP. So this is the transformers library I was talking of. So he's using the transformers library. He's getting the distilled BERT, the tokenizer. I talked of the model and the tokenizer and the heads. These are the 3 things you have in that library. So he's getting the pre-trained weights, the uncased distilled BERT weights into this. He's getting the tokenizer. He's getting the distilled BERT model class. And post that, he's created the tokenizer with the weights initialized. Sorry, the model. and everything is downloaded. And first step is to tokenize the sentences. Now, the tokenizer is called, and essentially you can see this is the sentence. It's been broken up and tokenized, and these are the numbers, the IDs that you've got for the tokens. And then I remember the padding I talked about, the classification token and all that has to get added. So and he's checking the maximum sentence length, and he's going to encode them with zeros or ones. He's reading in a file of the sentiments. And he was using only 2,000 sentences from that data set. So now loading the BERT pre-trained model. See, it's 200 something MB. BERT is 200 something. It's still not as good as MobileNet, which is just 14 MB, but still better than tokenize. So then the padding. Then the masking piece. So I talked about this, right? That the padding added to the sentences have to be ignored, that the sentence is already finished. So you have to tell BERT that. And now essentially we are ready. We have these sentences, we have the encodings, and we have their labels. We need to, now what we're going to do now is we're going to run, inference using this. No grades is because this is PyTorch code, and no grades means I'm doing inference. I'm not calculating any gradients or anything. I just have to evaluate this model, and I have the final hidden states after this as I execute this model. So it's all done. This takes a little bit of time, but not too much. I think. Maybe about a minute, because it's 2,000 sentences. So what will we do after this? After this, we'll get in basically a 768 element vector, which we will then pass into a classifier and just have a simple dense network. And that will just do the sentiment. Actually, in this particular case, he's just passed into a logistic regression model to do a classification. But we could have passed into a neural network as well. That's all he does. I mean, it's just connecting BERT. So you can actually now use BERT. I mean, it's that simple.
So Anirban, while we're waiting for it to load, I'll jump in with a couple of questions.
Yeah, sure.
We have a couple of questions around receiving the link to this demo, as well as your slides in general and the recording of the session. So to those of you who have asked, we'd be happy to share the recording of the session and the PDF version of the slides with you. If you drop us a note at events@zinnov.com, we'd be happy to share that with you. But in terms of this link being publicly available and this demo, Anirban, I'll just let you comment.
This demo, if I said, look at this search, Google for illustrated transformer. And if you Google for illustrated transformer, there's a guy, Jay Lamar, I think. So this guy has this demo, and you will find this in that article, I think, illustrated transformer. That guy has it somewhere. So I think it has finished. It has got, now what comes out is a base model output object, from the Hugging Face library. And that object has certain, different elements. It passes you the attention vectors, and we only want the first element of that object. So, and if you see, this is very important that each of these arrays is it's a tensor that has come out, and there are 2,000 rows. So each of these is like one row for each sentence, and there are 768 hidden units. So and there are 66 position tokens. So you've got a tensor considering all of these things. Now, why did, so what you can see the shape of this. There are 2000 sentences and a 768 element vector that I have got by taking this zero is because of I need to read the hidden state, which is in the base model output object. If you Google it up in Transformers library, the first element of that object will give you that. And then I want the last, essentially this part, that only the first position token I want. And I want it for all the sentences, and I want it for all hidden unit outputs. So once I have that sentence, I kind of just do, at that point, I just do a logistic regression, and that's pretty much, there's nothing new here. And so I have a 768 element vector. I took the classification tokens output, only that. And then I will feed it into a sentiment classifier file, a logistic regression thing. And pretty much that would be it. It'll give me, I think it's done. So it gave me some 84%. See, it 85% now. And this is untrained BERT. I have just done nothing to this is not your, imagine in your company, if you had to go ask some team, give me label data, they have no time. But this is untrained. I just took this and I put it onto this. It gave me 85%. That's the beauty of this whole thing. So that's it. Pretty much my demo is done.
Okay. So I'll try to cover every question before closure. But my first one for you, and it's something that you spoke about earlier as well, but especially because Transformers as a deep learning model is relatively new. I think it was only introduced in 2017 or so. Is there a need, in your opinion, for organizations or teams to unlearn specific ways of operating to fully leverage attention with Transformers?
Yeah. So as I said, that it's possible that convolution operations in image, even image processing, the vision part, could start using transformers heavily. So maybe at some day we could see that convolution go away altogether, like that vision transformer paper. Previously, Facebook used convolution and then passed the output to transformers, but it may completely go away. So it's hard to tell what will happen, but it could happen. So that is one thing to unlearn. Your whole maybe BGG16 may be a different thing now. Yeah. And industry-wise, there's one thing I see, that the move away from support, the support model, that whole thing today for companies, technical companies, the tech support relies heavily on a team looking for documentation and giving responses. We might see that with this ability to have pre-trained models for language, you could very quickly index and train chatbots, which intent classifiers, which could actually do self-support and greatly reduce the load on these teams. So self-support might become a theme. Further, the UI interfaces might start becoming less important, because your phone could just talk to you and understand what you're saying far easier than today, perhaps. So that's another thing.
Okay, absolutely. And just to your tech support point, because that's an industry-wide change that we're seeing in dependency, at least as of now, and there is really no barrier on which kind of industries can end up picking up, NLP and transformers and leveraging this, right?
Right.
Got it. And something else that you were talking about in your presentation was the introduction of transformers and subsequently pre-trained systems like BERT, changing the way you personally ended up working and learning, right? And so to that point, I just want to extrapolate and ask you what organizational practices you think have changed with the introduction of NLP as technology. Specifically unique to the Indian context, are there any key facets of NLP that you feel like organizations must keep in mind?
So in India, it's a different thing. See, for English, it's very easy. You take the Transformers library, and yeah, they do have one Hindi model as well, I think. But in India, there are so many languages, and only 10% of India speaks English. And what I heard some friends say is this year the startup theme is Bharat, I think, and Business Today also had an article on this. So they would have to train from scratch, and that's not an easy task because you would need a TPU, you would have to train Indian languages from scratch. And writing tokenizer is also tricky. You would have to start with a tokenizer, and there the Transformers library has an article on how to do it, but you'll probably start with a byte pair encoding tokenizer, and you'll have to decide on your corpus. And the bigger the corpus, the more accurate your subsequent predictions. Uh, that has been proven again and again. So anybody who has the large resources of GPUs and TPUs will be ahead of this game. I know in India, IBM Watson has done a Hindi tokenization. I think they've done some work. IIT Bombay is doing some work, but I'm not more than that. I don't know.
God, I was reading at the end of a couple of weeks ago, at the end of 2020, that Oxford Dictionary announced Atmanirbhar as one of the words of 2020 as a year because of COVID. So I think, yeah, you're absolutely right in terms of dependency on Hindi language is also going to increase, and maybe that's something that organizations need to keep in mind. So thank you for that. I think so I have a lot of audience questions coming in, so I'm just going to switch and ask you a couple of those.
Okay.
The first one being in relation to the first couple of slides that you'd shared, are there any limitations on text string length when you're keeping in mind transformer speed?
The thing is, as I said, that if you're reading a whole book, it becomes n squared, right? And you have to change your architecture. If you're doing protein sequence related thing, that time you will have to use the performer architecture or the reformer. Reformer is actually readily available on the tracks library. So this is not the only option. Hugging Face is not the only option. You can use the Google Tracks library, which is an alternative to Keras. This has a reformer architecture. You can find these models there as well, I think. So there is a limitation, but you can also surpass it.
So another subsequent question to that is, what does reformer or longformer mean in the context of BERT?
No, these are attention architectures. BERT is one kind of BERT is bidirectional in the sense that each word was paying attention in both directions. There was no masking. And reformer is just trying to address the limitation of attention. That attention, if you go beyond a certain number of words, it becomes n squared and it becomes slow. It won't scale up. So the thing is that they're just different variations of the transformer architecture. Some people took the encoder part, some people GPT has taken the decoder part. They've run away with different parts of it and tried to do things. So they're just different flavors.
Got it. Another question on BERT here is that given that BERT has pre-trained embeddings, wouldn't it not work in certain contexts? For instance, when dealing with a field that has its own specialized vocabulary.
Very good question. Yeah. Very good question. The fast.ai people had a paper on this that, when I said what we just did, we didn't train the BERT for that particular domain. Like our company, Akamai, when I was trying to do search and we had to index the support team's documentation, they may have a different language, or products may have a different language. And so it's good to do a pre-training on that. And so just taking we haven't done a mass language training on this particular corpus. I'm just taking BERT as is, like what we just did in the demo. That still gave me 84. Perhaps if I had trained on that, the sentiment reviews and I trained it more, I would have got better accuracy. Yeah, there is a paper by the fast.ai guys, look it up. I don't remember the name, but it's about the same problem, that fine tuning of language models.
Got it. Thank you. Another question, and feel free to please filter your answer as you see fit, is can you please speak about the use cases that you are working on related to NLP and Akamai Technologies?
So I came across this NLP as part of my search. It's not part of my daily job, but I did a search project, and there we had to index and we had to classify. And accuracy improves if you can label the documentation and kind of say this is this type of a document, because we can tag it by product so that the support staff finds it quickly. So I'm trying to do something more for India management where I could use attention at looking at the logs of Akamai. Some issue happens with the customer. We find it out perhaps by looking at the logs. Can we predict that it's going to happen basically based on certain parameters? Can we pay attention to those in the logs? And so that's what I'm interested in. But right now, I'm not working in the NLP domain as such. Attention can be used for many things, as I said.
Got it. So another question is transformers architecture in NLP is somewhat natural, and recently there are some studies around using transformers for computer vision. But that's harder to get an intuition for. So could you explain any thoughts around the usage of transformers in computer vision?
So then there is a slide, if you can project it, or let me see if I had one slide from the Facebook team where their computer vision, the object detection task was done using transformers. And as I said, okay, I'll have to go through it very quickly because
No worries. Sobhan, is it possible for us to share the deck from our end?
I'm trying to go find it. Hold on, I'm also trying to find it.
Yes,
Okay,
I
no
have
worries.
shared the you can present. I have made a present.
Yeah, it was object detection with transformers and
So I think you have presenters rights, Anirban,
okay,
if you
I'm going
could.
to present. Hold on a second.
Sure.
Okay, so this particular slide is what I had for this. Sorry. So on the one on the left, that this is how what they did is for vision, you pass your images through a normal CNN as it is, like you do regularly. Then then you basically end up getting you introduce some positional encoding as well into that output of the CNN block, and you have a concept of a query. So again, there's an encoder here which is taking in that input, and then again there's a concept of queries, which are essentially it's a bipartite matching problem. You have a set of queries, and you have a set of some findings from this image that there are possible certain blocks where some object could have been detected, and you try to do a bipartite matching, saying given this object and this the bounding box of that, which one matches, and that bipartite matching thing is done using the attention thing. And again, it's the paper link is there. If you share this, I think I think then you will have to share this full presentation. They can look at this link and read this paper.
Sure. No worries, we'll do
Thanks.
that. Thank you, Anirban.
Okay.
So I think a couple of questions around this. So I'm just going to try to maybe club them together. It's more about the use of nouns and pronouns in a sentence. So if there are multiple subjects or nouns in a sentence, and there's a pronoun like it that refers to one of them, how do you know what it refers to? And they've given an example which I can.
I know there is an example that Lucas Kaiser says in a video that I didn't put the trophy in the bag because it was too big. Now, is it the bag that is too big, or is the trophy that is too big? And so I don't have an answer to that. Yeah, I've tried actually running that phrase, and Google did, even the translate that is there today, it did make a mistake. So yes, it depends on the language. Yeah.
Absolutely.
So I'm sorry, I don't have an answer to how would I solve that yet.
Got it. No worries. I think for now it's just trying to avoid the usage of multiple pronouns, but absolutely. And thank you for that. Another question is around using BERT and GPT. Most of the computations are predefined on the way that the model should work. What is the need or use of knowing the maths behind it? Because if we understand the math behind it, does it help in getting to know the model better?
As I said, this is the concept of attention applies. You can do many different things. If you can use BERT, okay, I have a library, I can just use it. Yeah, true. But if you understand the concept of attention, then you can apply it to anything. You can apply it to your log data, your performance of your machines on your cluster. Like something's going wrong, you know it's going to happen, what's going to happen. So the concept of attention goes beyond just NLP. So that is at least my area is not just NLP. In fact, I'm just self-taught, and so that is the thing I'll say. You can go beyond BERT if you just learn the concept as well.
So because you mentioned that you're self-taught, and there are a couple of questions around this as well, could you recommend some good sources that will detail the inner working math of attention layers or transformer architecture?
Yeah, so yeah, one thing is illustrated transformer, Google for illustrated transformer. It'll do whatever I said, it's visually showing that. Then there is Harvard, Harvard or something. Harvard has the annotated transformer. Search for Harvard annotated transformer. That'll give you code, working code. It's in PyTorch, but you can follow it, I think. So At least I'm not a PyTorch person, but you can follow it. So those are two good links because there's code implementation of the transformer. Where else? Yeah, I think those are the two main ones. Then there is semantic relationship. I think is Lisa. Somebody from no, I can't remember this now. I have given some links in this. They can look at this link.
No worries.
Index
No worries. So just to recap.
At the end of the slide.
No worries. So the two you mentioned, number one was Google for Illustrated Transformer, and number one was a Harvard. If you Google Harvard Annotated Transformer, you'll get working code in
Annotated
PyTorch.
Transformer, you will actually get code.
Perfect. Thank you so much. And we'll also refer to a couple of links on the slides that we send out. Another question is whether XLNet is better than BERT in your opinion. I'll pause. There are a couple of subparts to this question, but I'll pause.
No, I actually haven't studied the XLNet architecture in detail. I have studied GPT somewhat, I know, but no, I have no comments on XLNet. But it's going to be more powerful, my guess is, because I think it has a lot more parameters. So it's probably going to be more powerful.
Got it. And then another question, in the same nature is how much improvement have you observed by using transformers in search over standard Elasticsearch toolkit? So
I have a slide for this again, but it's they can search what Google was trying to do. I'll give that story that by taking your queries and passing through it through a transformer, essentially just having words and doing TF-IDF and term frequency and document frequency, those codes for matching relevancy, which we did in search, it can be improved by tagging the document correctly and understanding the query semantically. So Google is doing is they're passing their queries through BERT. And so I want a visa from Brazil to, they give that example on their side, Brazil to New York, US visa. And they would initially show, the US, they would show the Brazilian embassy site because they would think somebody's going to Brazil from the US. But the concept of Brazil to New York or Brazil to US, they couldn't understand it. Now with BERT, it can understand that query. It will actually show the US embassy as a result far above than the other Brazil results because it knows the person is going from Brazil to the US. So it's able to.
Got it. Just knowing that down. Thank you. So another question is around throwing some light onto CNN applications or recent developments of CNN applications using transformers, if you have any.
That data is all I have. I haven't read too much. That the Facebook paper, object detection, they can read that, or the vision transformer paper. Those are the two papers that suggest.
No worries, and it should hopefully quote the same. Another question is how can we make and this is actually very similar to something we were discussing offline before the session, Anirban, but how can we make the output of transformer models more explainable to business? Because business needs to understand black box models, something similar to G.A.P and LIME for traditional models. So I'm assuming this is also referring to building a business case for usage of transformer models. Do you have any inputs or any advice on how we could do that?
No, I have not studied explainable AI too much, so I'm sorry, I can't answer this. It's beyond my knowledge.
Fair enough. Another question around what is the dependency on the number of encoders or decoders in the model and the length of the input sentence?
No, the stacking of it is more to get the depth in the sense that you can combine the meanings. Otherwise, each of these models had a different kind of input length. The original transformer, I think, had 512 tokens, and then I think GPT-2, I think I had some notes. GPT-2 kind of increased it to 1024, and I think the GPT-3 is much bigger. So it's a different thing. It's going to increase your processing power, obviously, as the number of tokens increases. But the stacking is more to get a higher level context. Just like in convolution, you keep stacking that. So it's the same thing.
Got it. And one last audience question before I move on to a couple of others is, any insights for handling bias and fairness for transformer models? Are there any tests which you are aware of that are used for this purpose?
No, I'm sorry, I don't know. Again, it's going to that same area, bias, explainable AI. I'm not very good at that area. So.
Got it. No worries. So what we'd also do is any of the other questions that we might not have time to get to, I will drop you an email with them.
Okay,
And if there's
I'll
anything
try
that
to
you might
find
be
an
able
answer.
to,
I'll try. Yeah.
yeah,
Okay.
just in case you have any links, any reference points, that would be great.
Okay.
We'd be happy to share that with the audience. A couple of questions that are also linked to something that we were seeing the audience ask, and we've spoken about this again before, is could you comment on the insourcing versus outsourcing of NLP transformer capabilities for specific teams in terms of when it might make more sense to outsource them versus build that capability in-house?
So if you're IBM and you have Watson, you can do it in-house. But I do not know if you're training a transformer from, like if you're training a language from scratch, like it's a new language. Suppose you want to do Manipuri or Odia or something. I think you would have better to do it on some cloud infrastructure because you will need TPUs and all. So I don't think you can do it in your own network. The other challenge is, which I faced in search, they didn't let us, our enterprise team didn't let us use Amazon Cloud resources for putting our support documentation there. So we could not do any complicated machine learning there. So it's a trade-off, but you can obviously do the BERT allows you to do a lot of fine tuning even with your normal in-house infrastructure. But training language model, you'll have to go out.
Got it. So just to kind of recap, obviously financial resources aside, a couple of other things that will be dependent on is maybe company regulations, sensitivity and customizability of information as well, basis of previous question. And then I think, you'd also touched upon if there's a high security requirement for your hardware platform, then you might not be able to outsource and it might have to be something that you insource. Is that right?
Right.
Got it. Great. So then just one more question around what are some key challenges that are faced by NLP or deep learning teams in India? And I think from your presentation, one that I could remember is dealing with long range dependencies would be one, and then obviously specialized vocabulary would be maybe another challenge. But is there anything else that you could share with us?
So you're talking of NLP related or general deep learning or both?
I'll keep it NLP, and then if there's anything else that you think is relevant, general deep learning, we can.
No, obviously you'll have, the big challenge would be big mixed language, right? You'll have Hindi and English mixed together. So you'll have to train for that. That'll be very difficult. Then again, there is an article on this in the tokenizer library. They can read up on the mixed language thing, but yeah, that'll be challenging, I suppose.
Got it. So I'll just recap. Number one would be long range dependencies in terms of super long sentences. Number two is actually the pronouns, the its that we still have to figure out how we can do. And then number three would be the language barriers and specialized.
Yeah, obviously the explainable AI concept is all. How do I explain how that engine is actually working? That's a very good question. That also has to be solved, I guess.
Absolutely, got it. And in the interest of time, just maybe one last question. That I'll ask from you, Anirban, is can you share any three pieces of advice or key takeaways for any center or team about to embark on their journey with NLP and deep learning?
Okay, in general, for deep learning is the same thing, that you should get a clear agreement on the success criteria for your project. Like if somebody verifying invoices and reading some text out of it, and the team expects everything will be done, and the business side, and you are saying only 90%, that should be clearly agreed to, that there will be some manual work always. And machine learning is very different, or deep learning very different from regular software, because you'll have to keep updating your model as things change. You will find new cases and you will have to address that. So there'll be some support staffing always you'll have to give to that project. That also you have to get a buy-in from. And you have to get a workflow right. I mean, the one thing I think in my search project was we didn't have a proper workflow for our documentation. I think that if we have it, we can do a lot more for all your data. If you have a good workflow, you can kind of build on it. That is an essential. So.
Got it. So I'm just going to repeat the three again for the benefit of our audience. I think number one was to get a clear agreement on the success criteria for the project. So what are you defining as your success metrics, as well as what are the requirements that you might need to source? So that would be number one. Number two is to get the workflow correct before you get into deep learning. And then I think number three, something you touched upon a little earlier, was the fact that it's very different from regular software development.
You have to keep finding new cases, and you'll keep fixing them. So there'll be some support staff. You have to get commitment from to get them allocated for this work.
Absolutely. So it's essentially, if I paraphrase, it's essentially an iterative process. So you need to
Yes.
make sure that it's constantly evolving along with the technology itself. Great. Well, thank you so much for your time, Anirban. I think that's all we have. There are a couple more audience questions coming in right now, but as I mentioned, what I will do is just drop you a note with all the questions we
Okay.
couldn't get to. And in case there is anything that you'd be able to share with our audience, we'd be happy to send it back.
Yeah, I've given a lot of links. If they read all this, they will probably be on top of all this. Yeah.
Great. So I'll just like to recap some of the links as well for the benefit of our audience. Number one, you did mention a fast.ai report or paper that has a lot of the answers in terms of pre-training for BERT specific vocabulary, etc. You talked about the Facebook case that you have in your slides. You spoke about Google for illustrated performer, as well as Harvard for annotated transformers for people to Google,
Yeah.
as well as the tokenizers library that they could refer to. Yeah. Okay, so I think that's
the Transformers library, and the link is in the slides. It's a
got it.
Yeah.
Got it. My mistake. Great. I will thank you so much. I think that's all we have time for today. It's been an absolute pleasure, Anirban, and for everyone listening in, I hope this session has helped in addressing some of the questions you might have had. We'll be happy to answer any additional questions offline. Please do drop us a note at events@zenove.com. We'll also be happy to share the recording as well as a version of the slides for your reference.
Thank you.
Thank you so much, Anirban. Take care, everyone. Stay safe.